Hello, welcome back to lesson 7. Today we're going to be doing more theorems for limits. These theorems are going to be very useful in computation for limits. So here's our first proposition to start us off. The limit as x approaches x naught of a real accumulation point of x is equal to x naught. Let's prove this. This is the identity function. For any epsilon greater than 0, there exists delta greater than 0 such that, what is their definition? Well, if 0 is less than the absolute value of x minus x naught is less than delta, then the absolute value of x minus x naught is less than epsilon. For a proof, let's fix epsilon greater than 0. Then the absolute value of x minus x naught being less than epsilon is implied by 0 less than the absolute value of x minus x naught less than epsilon, which we choose to be our delta, and we're done. Very trivial case, very easy to do. So now let's move on to real limits of monomials. So here we're going to be considering the case where x to the n, where x is a natural number. So the limit as x approaches a real accumulation point of x to the n is equal to x naught to the n. We're going to be using proof by mathematical induction. So if you haven't done that before, bear with me as I'll try to explain it all. There are two things you need to do. First, you have to write a base case, and you have to put an inductive hypothesis. Your base case will be for the first natural number that you want to show. In this case, whether we're assuming n is if 0 is a natural number or not, if so, the case for constant is trivial. You can prove that yourself probably. And we already did the case for the identity function, so let's just do n equals 1. The limit as x approaches x naught of x by proposition that we just proved up here is equal to x naught. Now number 2 is our inductive hypothesis, and this is where the proof by mathematical induction comes into play. Let's assume that only up to n, but up to n, the limit as x approaches x naught of x to the n is x naught to the n. Even if this n is only 1, we've proved that there does exist an n that it works for, okay? Even if that n is 1. And it's implied that for any other n plus 1, n plus 2, or anything else, it's implied that at n plus 1, this does not work. So n plus 1 is the minimum value for which it does not work. Not the only value, or not the only value necessarily, but one of the values that it doesn't work. So let's assume that. And we're going to try to prove that this is not true. So we're going to assume that the limit as x approaches x naught of x to the n is equal to x naught to the n. Then the limit as x approaches x naught of x to the n plus 1 is equal to the limit as x approaches x naught of x to the n times x. And by our product rule, the limit of a product is the product of the limits. And by our hypothesis, x naught to the n times x naught, which is the proposition we for the identity function we proved up here, which is equal to x naught to the n plus 1. Or in other words, the limit as x approaches x naught of x to the n plus 1 is equal to the x to the n plus 1. Thus, it is not true that there exists an n that is a natural number such that the limit as x approaches x naught of x to the n is not equal to x naught to the n. There is no minimum value where this doesn't apply. Or in other words, by using some mathematical logic, there does not exist is the same thing as saying for all n that natural numbers, the limit is equal to. So we go from there does not exist, where the limit is not equal to there for all n, it is equal to. This is a proof by mathematical induction, very useful when dealing with natural numbers because of their properties. So theorem, real limits of polynomials, another big one. If p of x is a polynomial of degree n, then the limit as x approaches x naught of p of x is equal to p of x naught. Again, all has to be real limits and real accumulation point. let's let p of x be this polynomial that we see right here, where a sub n is not equal to 0. Then the limit as x approaches x naught of p of x is the limit as x approaches x naught of the following. By our linearity theorem, we can factor out the constant, right? And take the limit. The limit of the sum is the sum of the limits, and hence by the real limit of a monomial that we proved up here, right? We can hereby conclude that this has to be true, and this is just p of x naught by what the definition of p of x. So we've proved that the limit of a polynomial function at a real accumulation point is just evaluating it at that point. Here's another theory.